Hello, my name is Michael Dick and I'm a Principal Research Scientist at Green Imaging Technologies, and welcome to this webinar. Today I'll be discussing some testing we recently completed on a dataless overburden NMR cell, like the one shown here, in an Imacore 3D rock core imaging system. The first experiments we did was to explore how much background signal the dataless cell has. The background signal in overburden cells is especially prevalent when you do experiments with short tau values like those used in shale samples. The first thing we did was to put the empty cell in our Oxford Instruments Geospec 253 magnet and decrease the tau value to 56 microseconds and recorded T2 distributions with these parameters. What you can see here is that there is 1.7 milliliters of background signal coming from the peak end caps, like the one shown here, if you center them in the field of view. But obviously this wasn't a realistic representation of how the cell would be operated under normal circumstances. You would always have the end caps separated by the height of a rock, like shown here. So we repeated the scans with the end caps spaced apart by 2 inches and 2.5 inches under these, which is more realistic operating conditions. And under these conditions, you see you get somewhere between 0.9 and 0.8 milliliters of signal. And finally, we remove the peak end caps altogether from the system, and you see that we have 0 signal when the peak end caps are removed. And this makes sense because the cell is made out of ceramic, which is NMR invisible. Finally, we took our results for 1.5 inch cell and scaled it to 1 inch diameter cell, like shown here. And the reason we did this was so that we could compare our background results with those reported by Daedalus for a 1 inch cell. And as you can see here, the Daedalus results are plotted in red, and they agree very well with our results under typical operating conditions. The next thing we did was explored the signal to noise ratio of the Daedalus cell when operated in an Imacore magnet. This slide shows 2 T2 distributions of a 100% saturated Berea sandstone, each recorded in the Imacore system at 1.5 Tesla using these scan parameters. All the data acquisition and analysis for this testing was completed using Green Imaging Technology system software. The blue trace was recorded with the rock out of the Daedalus cell, while the red trace was recorded with the rock in the cell. As you can see here, the signal to noise ratios for each are very similar. So the cell didn't have any effect on the signal to noise ratio in this experiment. It should be noted, however, that the cell was not connected to any pumps or flow lines yet. And as you'll see on the next slide, once you add flow lines or pumps to the system, the signal to noise ratio will decrease. To further explore the SNR of the Daedalus cell, 3D images of the same saturated Berea sandstone were also recorded inside and outside the cell. And again, we're using Green Imaging system software to record all this data. These images were acquired using fast spin echo pulse sequence using these scan parameters in the Imacore at a field of 1.5 Tesla. This slide shows 2D projections of the 3D data I showed on the last slide. Also shown is a comparison of the signal to noise ratio for each data set, as you can see here. When we normalize the SNR to the same scan times, you see that the SNR of the data recorded with the rock inside the cell is about 25% worse than when the rock is outside of the cell. And a couple things to note here are that the cell in this case was hooked up to a pump and flow lines, and this explains why the SNR has reduced as compared to the T2 distributions I showed earlier, when the cell wasn't hooked up to a pump or flow lines. Secondly, as you can see here, the total acquisition time is over 2 minutes for both these sets of data. However, the majority of that time, 2 minutes roughly versus say 39 seconds in this example here, is actually spent loading the gradient table into the console. This is a limitation of the current EVO console, but has been updated in the latest firmware update. The final set of experiments we completed with the dataless cell and the Imacore system was a flooding experiment. The ability to image floods in real time using this cell and the magnet make this system a very powerful tool for core analysis. The flood we did was a simple one where D2O was used to evacuate water from a fully saturated Berea sandstone. The D2O is NMR invisible, so the replacement of water with D2O via the flood is represented by a decrease in signal intensity. A series of 26 fast spin echo scans were recorded during the flood. Here's a few examples of a few of those spin echo images, and these are the 2D projections of the 3D data. The scan parameters used were the same as those employed in the last series of experiments in the signal-to-noise ratio examination. For each image, a fraction of a pore volume was injected, and then we would stop the flood, record the image, eject a little more D2O, stop the image, stop the flow, record the image, and so on until we recorded 26 3D images. And then we stitch these together to make a movie. So this movie shows how the data can be manipulated and rotated so the flood can be viewed from multiple angles. The movies were generated by outputting each flooding scan to 3D TIFF files using GIT system software. The TIFF files were then stitched together to make the movie like the one that just played using MATLAB and its image processing toolbox. The next movie again shows the flood in 3D, but also shows the projections of the data onto each of the XZ, YZ, and XY planes. So the 3D movie and the projections are coincident in time. The third and final movie again shows the flood in 3D, but it also shows the flooding of the middle slice in both the XZ and YZ planes projected onto the 3D image. This is an interesting way to show your data. So thank you for watching our webinar, and if you have any questions or comments regarding today's topic, please feel free to email us at info@greenimaging.com. Thank you.